Okay, here's some graphs that we're going to consider here to determine whether or not the graphs are differentiable everywhere. So in this first case, I have the classic function of absolute value function. First question is it continuous? Sure. Is it differentiable? No. At the point 3, excuse me, negative 3, the function is not differentiable because at this point on the left-hand side, the derivative is negative, in this case exactly negative 1. The right-hand side, the derivative is positive 1. So since there's such a dramatic change from negative 1 to positive 1, it's considered not differentiable. So therefore not at x equals negative 3. X values of which f is differentiable, so that would be negative infinity to negative 3, negative 3 to infinity. Next, I have a rational function. Is a rational function continuous everywhere? No. There's a vertical asymptote right there. Is it continuous there? Nope. So we say at x equals negative 1? Nope. At x equals negative 1. If it's not continuous, then it's never differentiable. So therefore, in this case, since it's not continuous at negative 1, it's also not differentiable at x equals negative 1. Describe the x values of which x is differentiable. Excuse me, that f is differentiable, so that would just be negative infinity to negative 1, negative 1 to infinity. I don't need the positive there. It's a bad habit. So much like the absolute value function, this is not called a corner, it's called a cusp when it comes together at it's a curve that hits at a corner. So obviously this function is continuous. So yes, it's continuous. Is it differentiable? No, for the same reason the absolute value function is not differentiable, because it hits this cusp where the slope changes from on the left and the right hand side at positive 3. So therefore not at x equals 3. So therefore, where is f differentiable? Everywhere except 3. Next one's a radical function. Radical functions are continuous everywhere on its domain. Obviously over here it's not continuous, but it's not defined over there, so that's okay. So really we're just looking at this function for x is greater than or equal to 1. So the question is it continuous everywhere? Sure. It's a nice smooth curve. Everything's fine. Is it differentiable everywhere? Yes, except for at one point. At this point right here. At that point right there, if you try to draw a tangent line, at that point your tangent line would be vertical. Well, what is the slope of a vertical line? Slope of a vertical line is undefined. So therefore, is it differentiable? Well, does the derivative exist? Which is the same question as asking, is there a slope at that point? No, there's no slope at that point. So not at x equals 1. So therefore, where is it differentiable? Everywhere bigger than 1. Here's a nice looking piecewise function. Notice a little bit of parabola and then a horizontal line. Since there's a jump discontinuity here, it's not continuous at x equals 1, so not at x equals 1. Is it differentiable? Well, the parabola is differentiable. It's a nice and smooth curve. The horizontal line is differentiable. It's a nice straight horizontal line. But is it differentiable at 1? No, because since it's discontinuous at 1, it's not differentiable either. So therefore not at x equals 1. Where is it differentiable? Everywhere except 1. Our next one is the integer function. So notice that, is it continuous everywhere? Well, obviously not. At this point, there's a jump discontinuity from negative 2 up, and then from negative 1 up, and then from 0 up. So therefore, it's not continuous. We're assuming that this function continues. So therefore, there's another piece here, and that there's another piece up here. So it goes up. So therefore, at every integer value, it's not continuous. So no at every integer. Is it differentiable? Well, if it's not continuous, it's not differentiable at those points. Is it differentiable in between? Sure, because it's just a horizontal line. That's differentiable, no problem. So therefore, no at every integer. Where is that differentiable? Everywhere except at x is an element of the integers. Or you could write x is not an element of the integers. And here's our last example. Here's a line with a hole in it, so it's a removable discontinuity. Is it continuous everywhere? Nope, there's a hole right there at 2. So not at x equals 2. Is it differentiable everywhere? Nope, at 2 is not continuous, so therefore not differentiable. So not at x equals 2. And where is it differentiable? Everywhere except 2. Okay.